Hey everyone, my name is Ashley, and today I'll be walking you through question one search intro from the CSM 61B worksheet on graph algorithms. So for this worksheet, or for this question, we're going to be looking at this graph below and writing the order in which the vertices will be visited using various different algorithms, starting from node A. We're going to break ties by alphabetical order, and we want to notice that there are edge weights introduced in the graph. So the first algorithm we want to use is DFS, which is for depth first search. And the idea behind DFS is that when searching through nodes, we want to follow down, search down a path of nodes or like a chain of neighbors until we reach a neighbor with like node with no neighbors, and then you propagate back up and continue searching for through the neighbors of other nodes. So I think the best way to explain it was like example. So pretend we're given the graph that looks like this. We're running DFS starting from this node. So DFS would pick one of these neighbors, so visit it, then visit one of the neighbors, and then until it reaches one with that's a leaf or has no neighbors. Since it reached one neighbors, it'll go back up to the last one visited, then go down the next neighbor. No, after that, it reaches another one with no leaf, we'll go back up, visit down the other path. So let's try to apply this concept on the graph we're given. So we know we're starting from node A, so we want to visit A first. So I'm gonna denote visit nodes with, by crossing them out and write it here. So visit node A. And then so we want to check what A's neighbors are. A's neighbors are C and G. DFS does not use edge weights, so we're going so they're essentially tied for which one is next to be visited. C is before G in alphabetical order, so we're going to visit C. After we visit C, we want to visit one of C's neighbors. So C's neighbors are D and H. And they're now tied for being visited. Notice we're not visiting G because G is a neighbor of A, and we're on C right now. So in this context, we're breaking ties to alphabetical order. So we go to D. We go down to D, and then now that we're on D, we want to check D's neighbors. D is directly connected to B and F, so we want to do one of them. So we're going to B, and then B only has one unseen neighbor, which is E, so we want to put that into the E. And in this case, we see that E has no unseen neighbors, so we want to go back up to B and see if B has any unseen neighbors that we missed. We see that it doesn't, so we go back to D. D has one unseen neighbor, F, so we want to visit that. F has one unseen neighbor, G, so we want to visit that. And then G has no unseen neighbor, so we go back up to F, back up to B, back up to C. And then we see C has one unseen neighbor, H. And at this point, we've visited all the vertices in the graph, so we can terminate the algorithm. So that's how you perform BFS on the given graph. So let's move on to BFS, or breadth first search. BFS has a different philosophy compared to DFS. So basically, it's from we want to search through all the neighbors of a given node before moving on to any other of any other nodes. So let's if we're starting from here, if we search both of the node's children before moving on to the next level's children. So it's, as you can see, it searches like layer by layer. So let's try running BFS on the given graph. So we're starting from node A again, so we want to visit A. And then we're given with the choices of C and G again. Since we're doing breadth first search, we want to choose visit all of A's neighbors. Next, we know it's either going to be CG or GC next. Since we're doing alphabetic order, we want to visit C and then G. We want to C, and then we want to visit the neighbors of the next vertex visit, which is C. So we want to C has two neighbors, D and H, and we want to visit those alphabetically as well. D and H, and then we want to visit the neighbors So that's all the unseen neighbors of C. We want to visit unseen neighbors of G, which is F. And I want to check the unseen neighbors of D. There are none, so we move on. Unseen neighbors of H are none, move on. Oh, my bad. D has one unseen neighbor, which is B. And so we want to visit B. And then we want to visit H's unseen neighbors, there are none, move on. We want to visit F's unseen neighbors, check there are none, move on. We want to visit B's unseen neighbors, there's one, E, so we visit E. And then at this point, we visit all the vertices in the graph, so we can terminate the algorithm. So for our last sorting algorithm, we're gonna be running Dijkstra's. Dijkstra's is different from the rest of the algorithms that we look at for it, in that it's an optimized algorithm. It's finding the shortest path between a given node, the starting node, and every other node in the graph. So just to give a quick explanation, Dijkstra's is finding shortest path between start and rest of nodes. It's hard to explain with the picture here because it requires edge weight, so I'm going to directly show you guys using by running on the graph below. So before we start, I'm going to write out every single vertex in the graph, and then walk through how we would initialize each vertex. So at the beginning, we set the value of the starting vertex to be 0. We're saying it takes 0 time to get to A, and infinite time to get to the rest of the places. So, and then we look at the all the values here. See, it has the smallest value. Want to visit, so we want to mark it as seen and visit. So we visit A, and seeing the path value to those, and checking if it's less than the value that we already have. So we say A has a value of 0, and it has a edge of weight to node G. So what this means is it takes 0 plus 2 time to get to G, which equals 2. And so the value of G right now is infinity. 2 is less than infinity. 2 is less than infinity. So we want to replace the value of G with 2. And then A is also connected to C. C has a value, the weight to of the edge to C has a value of 4, so it'll be 0 plus 4, which is 4. And then we want to run algorithm, the next step of algorithm, by checking which one has the lowest value and run it again. So we see G has the lowest weight here, so we want to visit G. And we want to check G's unseen neighbors. So we see G has a path to F of weight 9. The path from A to G was 2, and G to F is 9, so it'll be path from A to F is going to be 11. And this makes this the current shortest path to F. So we run the algorithm again. We see C has a lowest value out of all 6 of our remaining vertices. Want to visit C. And then when you see C's neighbors, which is D and H, the path to D has a weight 1. So it would be 4 plus 1, which is 5. And then we want to visit, which is 6. And so we both of these are less than infinity, so we want to update the values in here. And then we want to check it again. We see D has the lowest value out of all the paths here, so we want to visit D. And then we check D's neighbors. D has a path to B, which is has a weight 2, so it'll be 5 plus 2, which is 7. So we can place that. And then D also has a path to F of weight 8, which would be 8 plus 5, which is 13. F already has a value of 11 as dictated by G, and 11 is less than 13, so we place the value at F. So we want to go to H and go to H. And H has no neighbors, so we don't update the numbers here, and we just pick the next solid, which is B. So we go to B. And then B has one unseen neighbor, E, which has the path has a weight of 1. Put E to be 8. And then E is the next, because that's the next lowest weight. And then at the end only F is left. The shortest path to F is through G, so we want to go through G and go to visit F. And at this point, we've finished writing Dijkstra's on the entire graph. So hopefully this helps you guys understand DFS, BFS, and Dijkstra's, and just hope you understand like graph search in general. Thank you guys for watching, and see you guys